All right. Well, hey, welcome to week 3 of Physics 208, Modern Physics. Um, Today's plan, we're going to go ahead and sort of wrap up what we were talking about with geometric optics, with refraction and all that. And we'll put thin lenses together today, so you can kind of see how that is done. It's not really that big of a deal. It's just you kind of have to just go from one to the next. Take the image from the first lens and it becomes the object of the second, and so on. So we'll do those, and then we'll talk about just some real things that use lenses and why they're designed the way they are. And then we'll move into chapter 3, and we're going to talk about interference, which to me is maybe the coolest thing about light, at least in my opinion. Anyway, but before I do that, any questions on the homework or anything? You did see, hopefully, that the homework set has been extended to Thursday. So at least it's not pressing for tonight. But is there anything you guys want to look at from, what are we on, chapter 2? All right, I will take that as a big no. Okay, cool. Well, then I'm going to hop up to the whiteboard, and we'll start talking lenses in combination. All right, so I'll be right back. All right, so let's just kind of remind ourselves what we did last time in terms of lenses, and specifically the formula for the thin lens. So when we've got a thin lens, and thin, I'm surprised nobody asked me this question, how thin is thin? It's kind of along those same lines of, how small of an angle do you need to do the small angle approximation? Well, how thin is thin? Thin, it needs to be thin enough that the thickness doesn't really affect, or it's pretty small relative to the radius of curvature. So we need to have something so that the radius of that circle is fairly large compared to the thickness of the lens. But regardless, if we've got a thin lens, what we saw was that we got exactly the same formula as the reflection in the mirrors, right? So we have 1 over DO plus 1 over DI equals 1 over F. And that F is the focal length of the lens. And whether it's convergent or divergent, it doesn't really matter. We still get to use the same formula. But I just want to remind you also, the sign conventions are just slightly different, right? And every time we do these, I'm going to remind you about the sign conventions because it's super important. In terms of F, it's positive if it's convergent, and it's negative if it's divergent. And it's exactly what it sounds like, convergent. The rays that pass, or parallel rays that pass through it, will come together at a point. If it's divergent, parallel rays that pass through it will diverge as if they're coming from another point. And in that case, that other point, we would give it a negative F. In terms of the radius of curvature, we don't really need that in this formula, but if you're going to use that for like the lens maker's equation, for the radius, again, positive means that it's convex, and negative means that it's concave. So this is opposite what we did with mirrors. Okay, so the R's are opposite. And then the DI, this one's also a little bit different. Positive means that it's on the opposite side. And negative means that it's on the same side. And when I say same and opposite sides, I mean as the object. Okay, so if your image shows up on the same side as your object of a lens, then that's a negative DI. So that's also opposite what we saw. And then the one other thing that I want to put on here, the other little formula, was for magnification, and we saw this as well. So M is the magnification. It's defined as the ratio of the image to the object heights. But what we saw is that it's just equal to negative DI over DO. All right, so let's go ahead and just box these guys because these are the ones that we're going to be using as we do our calculus. All right, so last time we did do an example. I think we actually did 2 examples. We looked at one where we were just trying to see where the image would be located. And then the other one, we figured out where a lens or where the object should be placed to get a certain result. But what I want to do today is I actually want to put 2 lenses together. So you can see what the process is when we actually have 2 lenses that are being done in sequence. So basically the light's going to go through the first lens, do whatever it does. Then that light is going to continue on and pass through the second lens. And we just want to see what the final result is. All right. But it's all going to come down to, again, using these formulas. These formulas, we don't care how many lenses we have. We're going to use those every time. Okay. So here's the setup. Let's say we've got 2 lenses and they're both convergent. Okay, so we're going to have 2 convergent lenses and they're going to be separated by 36 centimeters. So let me just start drawing the picture here. So here's lens number 1 and here's lens number 2. And they're 36 centimeters apart. Let me give you the focal lengths for both of them. Since they're both convergent, the F's are going to be positive. So let's say that this first one has an F of plus 8 centimeters, and the other one has an F of plus 6 centimeters. All right, so we've got our 2 lenses together. So you could think, I mean, this could be like a little eyeglass or something, right? It's 36 centimeters long. We've got one lens here, we got the other lens here. We're going to look through it. Okay. All right, so let's get an object. And let's say that our object is located to the left of this lens. We'll have it upright. And I'm going to give you a height for it. Not that that actually matters, but when we, no, let's not worry about that. Let's just go with how far away it is. And let's say that this is 12 centimeters from the first lens. All right, so here's the question. Twofold, 2 parts to this. The first one's going to be, where is the final image? Meaning, where does it actually end up when we're all said and done? And what's the total magnification? Okay, so when you have multiple lenses, all you got to do is do them one at a time. let's just follow through what happens with the first lens. Then we'll see what goes on after that. All right. So when you've got a multi-lens thing, just start with the first lens. Forget about the second one just yet. So we're just going to look at lens number 1. And let's write down everything we know about it so that we can use our formula. So we know that the F is a plus 8 centimeters. We also know DO, right? Because we're 12 centimeters away from the lens. So is it a plus or minus 12?
Minus, right?
Okay, so minus, right? Why minus? Ralph doesn't agree. Ralph just put in the chat box plus.
I don't remember, so I was just guessing.
Okay. Well, you had a 50-50 shot, right? It's not terrible average or terrible chances. Okay, so that's not right. Excuse me. It is plus. All right, so Ralph just put in the chat box, since it's real, it should be plus. And that's absolutely correct. Since that's a real object, the light rays are coming from that object. It's real, so it is going to be a positive. So that object, its distance is a plus 12. All right, so we can actually use that to figure out di. So if we go to our formula, we're going to get 1 over 12 plus 1 over di is equal to 1 over 8. So you calculate this, you get di equals 24. I'll let you do that on your own. And it's a plus 24. So where is that image? If it's a positive image, which side of this lens is it on? All right, so Ralph just put it in the chat box on the other side. So the image is going to be located (24 centimeters) on the other side of the lens. It's going to be a real image, meaning we could project it onto a screen and we could actually see it. Okay, so there's that guy. In order to draw my picture, because I want to do it semi-decently, let's figure out what the orientation and magnification is for this one real quick. So if you go back to your magnification formula, the magnification, it's minus di over do. So it's going to be minus 24 over 12 or -2. So that means that this image is going to be upside down because it's negative, and it's going to be twice as tall. So that's what it's going to look like after it passes through the first lens. Okay, so no big deal. We did these before, same. But now we've got our second lens. And so we need to go through it. But we're going to follow the same process. We're going to write down the F's and the DOs and all that good stuff. All right, so F in this case is going to be 6. What's DO? All right, so Ralph just put -12 in the chat box. What do you guys think? Is he right?
Yeah, I think so.
All right, so you got a rousing endorsement there from Victor. But yeah, I think so. Okay, well, the way we're going to answer this is exactly the same way we would have answered it otherwise. We got to figure out, first of all, where is this image? Because this image is now the object for the second lens. So where's this image in respect to the second lens? And that is 12 centimeters away. Okay, so then we know then the DO is either plus or minus 12 centimeters. So Ralph suggested minus. Victor gave him a, yeah, probably, I think so, maybe. What do the rest of you guys think? All right, so Jesus is on board, which means if we're going to just go with majority rules with our vote, we already have 3 votes for -12, which would make it the winner. Yeah, but luckily this is not a democracy. It's a benevolent dictatorship.
See, I was thinking it wouldn't be negative because it's still a real image. It's just in a different spot now with respect to that lens.
And that's exactly how we want to think about it. Even if you were to go with, well, the first lens doesn't exist or whatever, and we're just dealing with the second lens. If this is our object, it's in front of the lens, which means it should be a positive DO. But even better, think real or virtual. Do the light rays pass through this? Okay, was it? Well, it was a real image, which means the light rays pass through it, which means it has to be a real object for the other one. Okay, so it turns out that the DO is still going to be positive. We're still going to go with a plus 12 on this guy. Now, it is possible that we would need a negative, but what would have to happen there, the kind of situation that would lead this DO to be negative, is if the image from the first one would have shown up on the other side of the second one.
Does that happen?
Oh, yeah. Easily. Well, like, what if this, instead of being 36 centimeters away, had only been like 10 centimeters away? So you bring that guy over here. Well, you know what? We'll do that. We'll adjust the position of the second lens so you can see how that would play out after we finish this off. But this image is actually in front of the lens. The light rays are going through it, and then they're going to pass through the lens. So that means that that DO is still positive. It's still a real object. All right, well, if we do this using the formula, we're going to get 1 over 12 plus 1 over DI equals 1 over 6. And that's going to give us DI equals 12. So that means that the image is going to show up here, 12 centimeters on the other side of the lens. And it's going to be a real image. While we're here, let's just look at what the magnification is for lens number 2 so I can draw my picture properly. So in this case, M is going to equal negative 12 over 12, which is -1. So what are we going to see on the other side?
No,
The
upside
image
down.
just upside down.
Okay, so it has to flip over again is the negative, but the same length. So this object, which was the image from the first one, is going to get flipped over, but the same height as it was here. Now I can't do that because I'm going to run off my whiteboard. And since I'm not at the college, I'm not going to do it. Basically, I'm more scared of my wife than I am of like the administration of the college. Anyway, so it's going to be upright, but it's going to be the same size as this image right here. So let's answer our questions. So where is the final image? All right, well, it's 12 centimeters to the right of the second lens. And then what's the total magnification? How does it compare to what we started with?
It's the same.
The same? Magnification is 1?
Yeah, it's double.
All right, Ralph and Victor just said 2. Remember, this magnification was of the second object, which was the first image. So if we kind of follow this, it got doubled in length and then kept that same length afterwards. So it's actually twice as tall as the first one. And so the total magnification is actually 2. What we're seeing is an object that's twice as big, but still oriented exactly the same way.
So basically that second lens acts like flipping the image. That's the only thing it does.
It just, yeah, it just flips it over. At least this, where that image was. Because if that image was somewhere else, the object length would be different, which then would change where the image length is for, or image distance for the second one. And then it would do something different. So the thing about lenses, when we say the lens does this, it does whatever it does to the specific object that we're looking at. Because if you change this object location, all bets are off in terms of what's going to happen. And the same thing, like if we're going to talk about a combination of lenses, you put those lenses a different distance apart, different things are going to happen. So it's not so much that a lens or a series of lenses does a specific thing. It will do a specific thing to multiple objects, or a specific object, I should say. All right, so in this case, it just doubles it. So it looks exactly the same, just twice as big, same orientation and everything. And the net result is a real image, which means we could actually project it on a screen. So what you would end up seeing with this is just a blown up version of this guy. So if we had these lenses set up this way, and we were to have some sort of an object that we were looking at, we would be able to project it onto a screen so that it looked twice as big. So if you think about it, there are lots of situations where we do want to magnify images. A great example is like a movie theater, right? Think about a movie theater, and you're going to go and watch Star Wars on the big screen. The image of the Death Star is way bigger than the object, which would be the piece of film. We go old school film. that has the little, the picture of the Death Star, right? That picture is like this big, just a little tiny rectangle, and yet it's, displayed on this huge screen. Well, that's because the projectors have lenses that do that. Now, I don't actually know a lot about movie projectors, so I don't know if they're multi-lens or single lens, because you can get away with the same thing with just one lens, but that might be a little bit more difficult. And then it'd end up getting inverted. So you'd actually have to have the film loaded such that the pictures were upside down. And then as it got projected through the big lens, it gets inverted. But this is the way that you can make those things bigger. And similarly, you can make things smaller by going in reverse, right? Like, here's the other thing about lenses. Anytime you do one of these things with lenses, you could totally backtrack. If instead I started with an object over here that was 12 centimeters on the right of these lenses, and I went the other direction, I would end up getting a real image 12 centimeters on the other side that's half as big. So if you want to make things larger or smaller, it's just a matter of inverting how this goes. Okay, well, before we get more into the other optical devices, let's hit that question, or what I was talking about, where the image from the first lens shows up on the other side of the second lens. So let's just adjust this ever so slightly. So instead of having separated by 36 centimeters, let me bring it in. So here's what we're going to do. Let's just kind of, we'll save most of this, but let's bring that second lens so that it's in here. And just for the sake of, I think, to get a nice number, let's change it so that they've only got a 12 centimeter separation. So we're still going to answer the same question. Where is the final image? And what is the total magnification? And you're going to see that it's not the same. We're not going to get the same magnification. Okay, so we can actually recycle lens one. All the lens one calculations are exactly the same because we didn't change where that object was. We didn't change the focal length or anything. So we still would have done this calculation and we would have figured out that the image would show up 24 centimeters away, which would be now on the opposite side of the second lens. But here's the thing. We're not actually going to see that. Remember, all the light rays, as they went through this first lens, we're going to bend and do whatever and form this image. But now those light rays hit the second lens and start doing the thing that they do for that. So it turns out that the light rays don't actually pass through this because of the second lens, which means for lens 2 now, again, our focal length is 6 centimeters, but our DO is going to be -12 because the object now is behind the lens. The light rays that would have gone to that object are hitting the lens before they actually go to the object. So this is what the setup would have to look like to get a -12 for our DO. But now that we've got that, okay, well, we still use the same formula as before. And you do the calculation on this, you get DI equals 4. All right, so where is that? And let's just say, look at the second lens. Is it to the right or to the left of the second lens?
To the right.
All right, so Bradley suggests to the right.
To the left.
Sorry, can you say that again, Victor? I was talking over you.
Left.
All right, so you think to the left? Ralph says left.
I'm gonna go with left.
Jacob says left. All right, so again, if we go majority rules, left is going to win. Man, Bradley, you're like the one dissenter every time. That's a good thing you did, because it's actually on the right. Okay, so this is going to be on the right. So now we're going to see our image actually. Four centimeters to the right. Okay. So why is it over there?
It's positive.
Okay, so it's positive, which means the light rays actually do go through it. We're going to get a real image. And the real image, remember what happened was the light that was coming from the first one hit this second lens, and the second lens took it and ran with it. And yet it's going to bring all that light to a place 4 centimeters away where we can see it. It means it's on the other side. Okay. Or just remember, if you have positive DI, it's on the other side of the lens. It's on the back side of the lens. And I know you might be going, but wait a minute, our object was actually on the right. And if we get positive, it's supposed to be on the opposite side. Well, remember that that object was actually virtual, right? It was virtual to start with. So it's already on the wrong side. Okay. But it is going to show up 4 centimeters to the right of it. So we're still going to get a real image. It's just going to be differently sized. So let's see if we can figure out what its magnification is going to be. We already know that the first lens was going to flip it over and make it twice as big. This one is going to be minus DI, so minus 4, over DO, which was a negative 12. So that magnification is going to be 1/3. So it's going to be 1/3 as tall as the image from the first lens. So remember, the image from the first lens was like way down here. So it's going to be 1/3 as tall. But it's going to be the same orientation as that first image, which means it's going to be downward. So that's what this thing's going to end up looking like once everything is said and done. It's 1/3 as tall as the one that was twice as tall, but upside down, and still upside down. Now, to help you out with the magnifications, because I know sometimes that's a little bit tricky, like doing the individual magnifications, no big deal, but I'm trying to follow it can get a little bit complicated. Turns out that it's super easy, like super mega easy. The total magnification, it's just the magnifications of the two individual lenses multiplied together. So if you go back and you look at that first one we did, where we had magnification of -2, the other one was -1. Multiplying those together, you get 2. And that was our overall magnification. So this one, its overall magnification is going to be -2 times 1/3, which is -2/3. So it's going to be flipped over, like we saw, and it's going to be 2/3 as tall. Because remember, it was 1/3, the thing that was twice as tall. So that gets you your 2/3. So you can kind of see why the multiplications go together. But I definitely want to point out that you can't use just a single magnification formula for this compound scenario. Because check it out, if you just took the original DO was 12 and the final DI was 4, -4 over 12 is not -2/3. Right. So when we have multiple lenses, we do have to take the individual magnification and then multiply them together. All right, so watch your signs. Oh, good Lord, watch your signs. Got to make sure that's what's going to get you, for sure. So remember your conventions. And basically, best way to think about it is in front of the lens, that's a positive object, but a negative image. Behind the lens, that's a positive image, negative object. Right? And then focal lengths, again, convergent is positive, divergent is negative. So practice your conventions, and that will definitely help you when it comes time to doing the homework and these kinds of problems. All right, so what do you think about this when we put two of them together? Thumbs up, thumbs down. Eh.
Reminds me of binoculars.
Okay, and it should, because binoculars do have a set of lenses. They actually do have a pair of lenses. They also have some mirrors in them. But yeah, this putting lenses together is a very common thing. We do it all the time. And it's why a lot of optical instruments work. So let's talk about that a little bit. But I'm going to go sit down because I don't know that I have a lot that I want to write up here. And this way I'm not like leaning into the screen. All right, so I'll be right back with you. Hold on. Okay, so now that we've sort of seen the basics of lenses and how they go together and what they do, let's talk about just some of the optical instruments we have and why they do what they do and how we're able to do things like telescopes and microscopes and binoculars and whatnot. But let's actually start easy. Let's just start with the eye. Okay, so just think about your eye. I don't know how much you know about your eye and the anatomy of it, but your eye has a lens. So if you look here, this is really creepy, huh? So in the dark part of my eye, in the dead center, in the black, the pupil, that's where the lens is located in your eye. And there are muscles that are around it, which change its shape. Like, have you ever noticed how you can't, for those of you who have good eyesight, because like I take off my glasses, I can't even
Like right now, I can't even read my screen, but I can if I squint a little bit, if I kind of change my distance a little bit. But your eye can actually adjust focus, right? Like think about this. Well, this happens to me all the time because I like to grade when I'm watching baseball. So I'll be grading. So I'm looking at something down here, and then I'll hear something happen in the game, and I look up. Right now, I can still see what's going on in that baseball game, even clearly, even though it's at a different distance than the papers or computer that were in front of me. Right. So I know you guys all have this experience. Well, if the lens in your eye was fixed, was rigid, you couldn't do that. You just couldn't, because the focal length is the focal length and you're done. So what's kind of cool about your eye is that it's designed in such a way, or it has been evolved in such a way that the muscles can change basically the shape of the lens, which then allow it to focus differently. So here's kind of what it looks like in your eye. All right, this is the general kind of shape of what's going on. So the eye itself is mostly circular. Right? And I'm just going to put a little thing here for the lens. Now on the back of your eye is what we call the retina. That's back here. And you can think of the retina as the movie screen. So the light's going to pass through the lens and project onto your retina. And then your brain interprets that image and everything's beautiful. Okay, so like, here's the deal. Let's say that out here you're looking at a tree. So think about what's going to happen as it passes through this lens. Now, it turns out that this lens is convergent. So the image is going to show up. It's going to be real, and it's going to be over here. If you just follow a couple of rays through it, so like let's think about the ray that goes through the middle. It's just going to project back here. And then if you were to go through the focal point, let's say that the focal point is right there. So we go through the focal point and then it comes back, right? So what we would see with that lens, where those two came together, would be something that looks like this. So our object gets flipped over when it becomes the image. And this right here would be a problem. This would not be focusing, because what we need for our eye to focus is this image needs to be back on the screen. Okay, well, this is again where I'm saying those muscles come into play, and they can adjust the focal length of the lens. And as we saw from that formula, right, if we just go back to that formula of 1 over DO plus 1 over DI equals 1 over F, right? Assume the DO is fixed, the tree is just, it's out there whatever distance. But if we fiddle with this focal length, we're going to get different numbers for our DI. And so your eye, the muscles in your eye, adjust to bring that guy back here. So that's why be reading a piece of paper and then look up and see something that's far away and then come back and look at your paper. Now, when you guys start getting older, you will notice that there's a little bit of a lag. I don't know if any of you guys are old enough there, if your eyes are that bad yet. But I notice it now for sure, that it takes a second for my eyes to adjust that lens. So those muscles are getting old and tired, right? You guys are still young, so your muscles, your eye muscles are probably nice and quick. But there's a little bit of a delay as it tries to focus. Okay, So now let's talk about these things. Because if you're like me, and I know that there are a couple of you that have lenses that I know that you use, I naturally have things out of focus. I'm what you call nearsighted. Like I can read just fine. Without my glasses, I can take this and I can read it, no problem, right? So when I'm in this kind of distance, everything is great. I can read that all day long. You start going too far away and I start struggling, right? Like if I were to turn around and try to read that whiteboard, it's going to be a little bit blurry. All right, so I'm nearsighted. Now, other people are farsighted, which is the reverse. Like you can see far away, but you can't really read. All right, well, that's where these come in. So let's think about what we just did, right? So come back to this picture that I've got drawn of the eye and everything. Let's put in some eyeglasses. So we're going to put a lens here, eyeglasses lens right here, right? So that's going to go up over our ear. But now we got a second lens. So we just put lenses in combination. So think about what that does. The light from that tree is going to come into this first lens and bend, which then is going to proceed through that second lens, the lens of my eye. And the next thing you know, the image of the tree is actually on my retina and I can see it. So anyone who wears eyeglasses, they're just designed in such a way to bend the light properly to assist your lens in your eye, which is a little deficient for whatever reason, and makes it so that you can see. So kind of interesting. And obviously you're going to need different shapes and different thicknesses and all that depending upon how much you need it to bend. If your eyesight is not very bad, you tend to have thin lenses because you don't need a lot of correction. You don't need a lot of bending. If your eyes are really bad, like my wife, is horrible eyesight, and her glasses are crazy thick, crazy thick. She wears contact lenses, so she doesn't have to worry about that. But you change the shape or you change the thickness just to do the bend, however you need it to do. And if you wear contacts, it's really the same idea. It's just that second lens isn't out in front of your eye. It's actually kind of residing right on the lens. It's not exactly on because there's some space between the lens and the curvature of the eye. But it plays the exact same role and does exactly the same thing. It just needs a different shape. All right, so that's a naturally occurring lens that does exactly what we want. But just think about this. Everything that you're seeing is actually upside down. It's being projected upside down onto your retina. But your brain knows to think, oh, that actually means right side up. I think that's really cool too, that the brain is that good at being like, oh yeah, this is all jacked up. It's a problem. And I've heard, now I haven't, like, this is total anecdotal, but I've heard that there was a study where people were told to wear lenses that flipped everything over. And after a little while, their brain was able to correct for that and everything looked like it was right side up again. I'd believe it, but like I said, I don't know for sure. All right, so that's how a lens works. So then let's think about like a telescope or binoculars. So let's just go to a telescope. I'm going to draw a real basic one here.
I have a quick question for you.
Yeah, go for it.
So you know how you stand up too fast, your vision can get blurry. Do you think that's like a muscle spasm within your iris due to, weird blood flow? Or do you think it's, just the sudden change of environment, your eyes trying to focus?
I don't think it's the, I think it is due to blood flow. And it's probably just like all the muscles that are, working the lens, all of a sudden aren't getting blood. And so they kind of like freak out for a second. Same thing like when you get lightheaded when you stand up quickly. That's my guess. I don't think it actually is that it's that different in terms of the light rays coming into your eye. You know what I mean? Because like if you're watching let's say you're concentrating on the television screen and you stand up, you didn't really change a lot in terms of the location of the screen relative to your eye. I mean, minor. I think the bigger issue is just the blood's not getting there because of, gravity and whatnot. But I don't really know. Okay, so let's look at a telescope. So telescope, of course, we're looking at some star that's super far away. But for all telescopes, there are going to be two lenses. Lens that's out at the end, and then there's the lens that's in the eyepiece. And they're designed that way so that you can change the eyepiece lens, which will get you different magnifications. It's a lot easier than trying to adjust this one out on the outside. But think about what's going on here. We're getting all these rays that are in essence coming in parallel because they're super far away, right? And they're all going to bend to the focal point of that first lens. So they're all going to come cruising through here. All right, well, then they pass through the second lens and they're going to do their thing. And they end up giving you what's kind of wild about this one is that they don't actually converge once you get all said and done. They're going to diverge. So we'll make them so that they diverge. This is going to be exaggerated divergence, but they're going to diverge. Now, think about what we're going to see. Your brain's going to see that divergence and go, okay, let me backtrack these. And let's say they come together right there. So what you're going to see is another star. It just appears closer. So I should probably make it look bigger. So think about it. If you've ever looked through a telescope, it still looks like the stars, the nebula, the moon, or galaxies, whatever you're looking at. It still looks like they're on the other side of the telescope. It just looks like they've come closer. So it turns out that that's due to a divergence. All right, but again, they're designed in such a way that these lengths are correct for the focal lengths of this big lens, so that when it reaches the eyepiece, it does this sort of thing. Now, usually what you'll see in a refracting telescope, though, is you'll have the eyepiece, and then you'll have the tube. Right? So it looks like that. And this just makes it so it's a little bit easier to see. But in order to make that happen, they also put in a mirror. There's a mirror in here so that the light, when it comes through the first lens, comes to that mirror and then bounces up. Basically what it does is it increases the length of this thing. So then if you have a reflecting telescope, those tend to be much shorter. Those are like the really big, fat, round ones. And have your little eyepiece. But the way they're designed is they've got mirrors in here so that the light, that it's usually like a little centralized mirror right there. So the light comes past that mirror, reflects, comes to that second mirror, and reflects again, and then comes out. Let's just say it comes out that way. And so in essence, what you did was you got the same length, because it goes 1, 2, 3 times that distance, as opposed to having to go all the way just this one distance. And the different lengths allow for different abilities to see, how far you can see and all that. And so that's the advantage of a reflector telescope. But it still has 2 lenses. It's got the lens at the start and the eyepiece lens. And then if you look at binoculars, it's exactly the same idea. And so there's our crappy binoculars. But it's lenses. And then it's got another pair of lenses here at the eyepieces. And the light rays do the same thing. It's just, it requires some mirrors for this to happen. So as the light comes in, it reflects off the mirror, and out the eyepiece. And what's great about binoculars is you can actually adjust these separately. So if your eyes aren't equal, you can change the focal length, the total focal length individually, still be able to see them. But the same kind of deal, that what it's going to appear to you is that that image is still over there, just closer. And microscope, same story, right? Exactly the same story. You're just looking things that are much closer than those that are far away. And because they're much closer, you have to change how you do it a bit, because everything is determined by that DO, right? And if things are really far away, like stars, the DO is basically infinity. So when you plug that into this formula, your DO is infinity, which means that goes away. So your image is going to appear at the focal length from the first one. As opposed to, again, if at your microscope, you're looking at something close, now that distance isn't infinite. So that thing doesn't drop to 0. But anyway, so there's a little bit about how all these things are designed, and it's really just making use of one equation. And you can fiddle with the focal lengths, and you can fiddle with the distance, specifically the distance between them, and get it to do exactly what you want it to do. Anyway. So I find this kind of cool, actually, that we have this much power over light. We can literally bend light to our will. We can make light do what we want it to, so that it's advantageous for us. All right, so there's a little bit more about lenses. Let's take a real quick break. I'm going to go and go use the restroom, but I'm going to pause the recording here. All right, so we're going to move into chapter 3, and chapter 3, like I mentioned earlier, is about one of the more interesting things I think about light. But up to this point, pretty much everything we've been doing hasn't really been treating light like waves, right? Like we've really been doing ray diagrams and kind of following where these things go and thinking of them as like particles moving along in those directions. So we haven't really hit the waveness of light so much, other than talking about how different visible spectra or the different colors have different wavelengths, right? But other than that, we really haven't hit waveness. Well, that's going to change now. We're going to start looking at some of the things that happen because light is waves. And light is kind of crazy because it's both a particle and a wave. It acts very much like particles. We haven't talked about it, but light is made up of these things called photons. And you can think of photons like little bullets of light. And so they're like little particles of light. So right now you're getting bombarded by those from all the different light sources around you. But light doesn't only act like particles, it also acts like a wave. And it's kind of trippy that it does that and that we can see it. But what we're going to talk about here in chapter 3 is all about stuff that comes from the fact that it's waves. And we're going to talk about interference. So go back to, I think it might have been second quarter physics. So a year ago, when we were first in this Zoom world trying to figure stuff out, and you guys were in here with me, and we were talking about waves. Do you remember what interference means?
It means when waves are overlapping and it either makes the amplitude greater or cancels it out.
Okay, yeah, and that's perfect. So you're right, Jacob. It's interference is just the waves coming together and reacting to each other. And they build upon each other, so you can actually get much larger waves. They can cancel each other out, so that you get no waves. You can get all kinds of stuff in between. But really, when we talk about interference of waves, it's just the interaction between two waves. So we already know that that happens, right? Let me draw a picture here. Let's get rid of all this other stuff real quick. But suppose that we have 2 point sources of waves. Okay, so one of them is going to be right here. And it's going to create a wave that's just, very regular. So it's going to send out wave fronts. Now, when I draw the lines here, these are going to be the peaks of the wave. Okay, so these are going to be the maxima. And so halfway between the peaks would be the trough, and pretend that these are circles. Right? But basically, these are radiating outward from this guy. Now, we're going to put another one over here that's going to do exactly the same thing. So it's going to get its little circles that are coming out, and these should all be equidistant from each other, concentric, but clearly I'm going to stop because those are getting more and more elliptical as we go. But basically, if you were to look at any of the places where these lines come together, so let me put some black dots at where these lines come together. This is where you're going to have the crest of the wave from the pink source meeting the crest of the wave from the blue source, right? And so these are going to be places where we have what's called constructive interference. And basically what's happening here is you're going to get twice the amplitude, assuming that the two waves were the same amplitude to start with, right? Those places, you're going to get constructive interference. Now, you don't only get that where peaks meet peaks, but you also get that where troughs meet troughs. So if we were to look at the points that are in between these, like exactly halfway in between the blue circles and the pink circles, right about there, those are also going to be places of constructive interference. Okay, so then the destructive interference, that happened where we ended up getting a maximum with a minimum, so or a peak with a trough. And so those are going to be places that are on one line, but halfway between the others. So I can do a whole bunch here. right? So these are going to get destructive interference. And here you're going to get no wave. They cancel each other out entirely. So I don't know if you remember this because we did this remotely and everything, but I had set up in my, you may remember in the old, my old house where I had the lab set up. I had a couple of speakers that were sending out the same frequency of waves, so the same wavelength waves. And then I walked around with the microphone. And do you remember how like there were places where it was louder and then quieter depending upon where we were?
I remember that.
Yeah, you do remember that? Okay, so at least somebody was paying attention back then. It's not quite like usually I do this in a classroom and have you guys walk around the classroom and you totally hear it. You're like, oh my God, I just went to a dead spot to a loud spot. And so we can find those places where the interference happens. Okay, so this is just how waves work in general. And light, since it's a wave, does exactly the same thing. When you have two sources of light that are the same wavelength, they will have places where they alternate having constructive interference and destructive interference. All right, so if we're talking about light though, what this means is where it's constructive, this is going to be bright, and where it's destructive, this is going to be dark. So you're going to get places where it can be bright and where it can be dark, depending upon where you are. But something that's really important here, and so it's so important, I'm going to write it down, that what we need here is the same wavelength. Okay, we need the same wavelength, which the term that we use for that is monochromatic. And to help you with that, you know how I like to give you like the breakdown of words. So mono, that's one. Chrome is color. I got a little funky there. So monochromatic literally means one color. And in the context of light, one color means one specific wavelength. Okay, so if it's monochromatic, you're going to have this. So imagine we're in a dark room and all we have are two lights that are sending out waves that are the same color, same frequency, all that good stuff. What we would actually see if we had like a light sensor is that there are going to be places where it's darker or lighter, depending upon which of these constructive or destructive interference points we're in, just like we had louder or quieter, depending upon where we were in the room when we had sound waves. Now, this is why you don't see this in like a classroom, because you think about, or any room where you've got multiple light sources, because you start going, okay, well, let's say I've got the two light bulbs on, and I turn them both on. How come we don't have that happen? How come there aren't places in the room that are dark due to interference? Well, that's because of that monochromatic business. If you think about one of these places, we get, say, destructive interference, right? So we come back to one of these. Imagine we're at that point right there. Let's pick a color. Let's say we're going to lose the wavelength of orange. Okay, Well, if orange gets destroyed there, that doesn't mean that all the other colors do. And in fact, even if you think orange, there are all kinds of wavelengths of orange, right? There might be the centralized wavelength of orange, but there's all the other ones. Okay, so you lose one of the many oranges, your eye's still going to see the rest of the orange. Never mind the fact that the green is still there and the blue is still there and all that. And so the fact that we have light that's not monochromatic makes it so that we don't actually see this. Okay, but it is definitely possible to see it. And I bet you money that Kathy's going to have you guys do a lab with this, because here's what we could do to actually see this happen. Let me clear the drawings here. What we can do is we can actually set up a little scenario here where we've got kind of a screen that has two holes in it. And what we're going to do is we're going to have a light source over here. Okay, so here's our light bulb. Okay, so that light is sending out waves. And think about what we know from Huygens' principle. Huygens' principle says that when light comes to just a point source, it's going to start radiating out circularly from that. Right? And then similarly, we're going to get one from the other side. And you can see we're going to start getting the interference pattern. We're going to get bright spots. Right, so here are some examples of bright spots in the pink. And we're going to get dark spots. I'll put those in blue. All right, so here are some examples of where the dark spots are going to be. But you notice that we get that kind of alternating pattern of bright and dark and bright and dark and bright and dark. Okay, so this is what we call the double slit experiment. And there was an English physicist by the name of Young. I don't know what his first name was. But he was the first one to do this, where he was able to send monochromatic light. In the lab, you're going to do it with lasers, because lasers are monochromatic. I think he did it with filters. He filtered out all of the wavelengths other than the one he wanted. But he sent light through the two slits and projected that light against a screen. And you can actually, if you go to Google or your favorite search engine and you just say, hey, find me the double slit experiment and show me pictures, you will see all kinds of pictures that show this. So hopefully you guys can all see my browser window now. And here's an example of a picture that was taken from the double slit experiment. And you can see these alternating bands of bright and dark. Now, I know you probably look at those brights and go, oh man, they're so much whiter than the darks. That's weird. Just realize that what you're seeing there is a gradation of light. It's brightest in the middle and starts darker. And then our eyes eventually can't see it anymore. But if you look over here, you can see there are all kinds of pictures that have these. Here's another one. I think this definitely shows it better as like points of bright and dark. Right? And you also notice though that the bright spots are not the same brightness. Right? But you can get there's all kinds of pictures of this, and you'll be able to see this. Oh, that's not actually real. Nice try, bang. Right? But you can find all kinds of these images. Now, you're probably going to do this in the lab, so I'm going to let you actually play around a bit with that.
Yeah, we
But
did.
Oh, you guys already did?
Yeah.
Oh man.
She spoiled it for you.
Fine.
Or I guess
All
for
right. Well, then never mind. You guys, and you tell me this now? All right, whatever. You guys suck. All right. So did you guys do the math behind it? Did she show you where, like, I'm sure you guys have a formula for figuring out where the bright and dark spots are.
Yeah, she gave us the equation, but she didn't go in detail of it.
Okay. Well, then why don't I do that?
I'm sorry that that bubble got bursted, but why? Who possessed physicists to try that experiment with electrons?
Okay. So spoiler alert. Oh, so did she tell you about that? Or
No,
you
I just know about that.
you know about that? Okay. So for the rest of you, because in case you haven't read or seen what Bradley's talking about. Okay, so this is a little bit of a spoiler. We're definitely going to talk about this later. It turns out that all matter also acts like waves. I think I might have already spilled that before. But when that was first proposed, when it was first proposed that matter has wave-like properties, you can probably imagine what the reception was to that, right? Whoever it was that first came with that idea probably got a lot of, dude, come on, really? Particles are particles. They're not waves. Like whatever you're taking, change the dosage because it ain't working, right? That was probably a lot of what the response was. So think about it. If you're going to go, okay, well, I want to try to show that it's a wave, you probably go to your bag of tricks of, okay, what are all the different things that we've seen that illustrate waveness? And then you start thinking, okay, well, which of those can I replicate with particles? And that's probably where the idea came from, to do exactly the same thing, but we're going to shoot electrons through these gaps. And when they did that, well, let me pull up the picture. Man, I am all out of sorts now. This is the problem with having a different physics teacher or class teacher and lab teacher. Or maybe Kathy and I just need to talk a little bit more. I don't know. I say a little more, maybe at all. She and I haven't coordinated this at all, which you guys know me is not a surprise, but Kathy is a little bit more, let's just say, on top of things than I tend to be. All right, so here's what they did. They said, okay, well, we're going to take what's called an electron gun. It's exactly what it sounds like. It's a gun that shoots electrons. Okay, it doesn't look like that, but there's our electron gun. All right, so pew, pew, pew. So we're just going to send tons of electrons here. Now, what you would imagine if electrons actually were particles, and you were to watch for where the targets, where they hit on here, so it's target practice. What you would expect to see is a whole bunch of hits right here and a whole bunch of hits right here. Right? Because that's going to be the bullets actually making it through the slits, carrying on to the wall. So if electrons were particles, this is what you'd see. Well, it turns out that that's not what they saw. What they saw was the same alternating pattern that you see with light. Now this isn't, bright or dark. It's just we have hits on our target or we don't. And this was one of the first direct evidence that particles actually follow or have wave-like properties. And then they did all kinds of fun things where they're like, okay, well, let's just cover up one of the holes. Well, as soon as you cover up one of the holes, that pattern goes away. The electrons just Well, because now it's just a single wave coming out one single hole, and you see the regular pattern. Anyway, it's kind of wild, but I'm going to guess back to your original question, Bradley, who, like, why would they have thought to do that? I think it really was, hey, we're trying to show that this idea that they are waves is valid. And the way you're going to do that is by trying to replicate experiments that show waveness there. So I don't really know, but that's my guess, at least.
I have
All
a
right, well,
question for you.
yeah, go for it.
You know how when atoms are trying to go into a higher energy state to require more electrons,
Uh-huh.
and they emit a photon sometimes?
Uh-huh.
Is that photon like the whole spectrum, or is it specific to the atom, the wavelength of that photon?
It's a very specific wavelength.
Okay.
And that I'm not going to spoil. That we're going to hold on to for a while. Because we know exactly what wavelength you're going to get depending upon the change in the energy. But that's very much further down the road. Meaning, I don't know, in a month, maybe a month and a half, somewhere in there. I'm going to guess that somewhere in May, we'll talk about that. All right. Well, since Kathy stole my thunder and actually showed you this, but it's kind of cool that you did see it. Were you tripped out by it?
Yeah, it's strange because it's almost so hard to refute that it's got to be like a wave.
Oh yeah, there's no question that light is a wave. It has to be. And the double slit is a great example of that. But all right, well anyway, that's one of the things when I go to elementary schools and show them physics stuff, just because, you know, once a teacher, always a teacher. And that's one of the things I always show. And the kids love it. They absolutely love it. They think it is the craziest thing in the world. And I'm like, it totally is. And then I say, but if you keep studying science, you'll see why.
Correct me if I'm wrong, but if it's the single slit, is it interfering with itself?
Single slit, yeah. If it's a single slit, the way to think about it, hold on, I'm trying to, close enough. All right, so if it's a single slit, here's how you need to think about it: as each of the points in this single slit are point sources for wave. And so they're each radiating out their semicircular things. And so different pattern because of that. And then if the slit is wide enough, you don't see it at all because there are so many wavefronts. And I just got a message that my internet connection is unstable. So if I drop out, I'll be back as soon as I can. All right. Okay. So just real quick, am I still with you?
Yes.
Yeah. Okay. All right. So let's look at the math behind this and why you saw what you saw in terms of the formulas and the things that you calculated in lab. So we're going to say that we've got a slit distance of D. And let's go with a distance to the screen of L. And we're going to be looking for where is this thing located. Right now, what I really should do is go from the midline. Okay. But let's look and see. We'll look at this and see why it has to be where it is. So to help us out, I'm going to draw another little triangle here. I'm just going to draw this guy. So that's a little right triangle. because if that L is really far away, and my picture is not really far away, but if L is real, or if L is really long compared to the wavelength of the light, then the difference in the distance traveled between these bits of light is really this right here. Okay, so that little pink bit, this is the difference in the distance. We're making an approximation that we're saying that those two, these two rays are parallel to each other, and they clearly are not. But if the screen is far enough away, it definitely acts as if they are. Okay, so if we're going to get a bright spot, that means that that distance, that difference in distance, has to be equal to a multiple of the wavelength, because we need them to be in phase when they come together. So to get a bright spot, we need that change in distance. Let me call it, how about delta big D? Has to equal some multiple of our wavelength. All right, well, if I want to know this distance right here, I can use the right triangle to help me. And if we look at the angle that takes us up to this point, call this guy theta. So from the midline up to where we see the spot, the bright spot, that's actually the same as this angle in the right triangle. So that difference in the distance, delta D, if you divide that by the slit separation D, that's going to equal the sine of theta. So we can equate these two things, and we get m lambda equals d sine theta. All right, so in terms of what the angle has to look like, the angle has to be such that we get this relationship. All right, well, we're going to make use of our small angle approximation. Because again, if this is really far away, if that L is really far away, then those angles are tiny. Like think about when you were doing this in lab, the distances to your bright spots were probably on the order of centimeters, right? If you were to go from the center to your bright spots,
Yeah.
centimeters. What kind of magnitude was the distance of the screen to the where you were projecting, the slits to your projection? Meters?
Yep.
Yeah. So, you know, you're talking, okay, so L is a couple meters, X is a couple of centimeters, right? You're looking at that angle is such that you're going, you know, over 100 and up 1. That's small, right? So we can use that small angle, which means that sine of theta is approximately equal to theta. And also the tangent of theta is approximately equal to theta. Like that's the key to the small angle approximation, which means that sine and tangent are virtually the same. So what I'm going to do is I'm going to rewrite this with tangent. And if we go to the bigger triangle that's got this theta in it, we can see that the tangent is equal to x over L. And if we solve that for x, we get L m lambda over d. And if you look at your lab packet that you got from Kathy, I'm sure that the letters might be a little bit different. But this was how we could figure out where that x was. and they're very regular, right? If I factor out that M, they're all multiples of that L lambda over D. And so if you look at from any one bright spot to the next bright spot, that distance is always the same. And that distance is equal to L times lambda over D. So that's why we're seeing them, and that's why we're seeing them nice and regular like. And so those are for the bright spots. Now, if we want to do dark spots, what changes? What do I have to change in this if I want to look for dark spots?
Theta?
So the theta will change. But think about what has to happen to get a dark spot. What has to be true about the two waves that come together there?
There needs to be destructive interference.
Okay, so there has to be destructive interference, which means I don't want whole number of wavelengths. I actually need that change in my distance to be off by a half a wavelength, or 3/2 a wavelength, or 5/2 a wavelength. But it's that half wavelength that's going to make it so that they destruct. So it turns out that the only difference, because everything else is the same, sine of theta is still this delta d over d, which is equal to the tangent, which is x over L, right? It just changes here that we get x equals L times lambda over d times m plus 1/2. But that's why there's always a dark spot exactly in between the bright spots, and the distance between dark spots is the same as the distance between bright spots, and so on and so forth. All right, well, there's at least the math behind it. So now you can see why you were seeing what you saw and how you can use that difference in distances to measure the wavelength. Right? I mean, that's actually what you can use this for. You can use this to determine the wavelength of some unknown light, because you can pass it through a slit whose, slit distance is known. So a pair of slits like that, or if you know the little d, and you know how far away it is from the slits to the screen that you're projecting it on, you can measure where those bright spots are and then backtrack and find the wavelength. Right. So kind of cool though. And I can just imagine the first time, Young did this, I bet there was a bit of awe. And I think probably the intent, I think this experiment was designed to show the waveness of light. And so it was expected to see an interference pattern, but I still think that probably the first time that Young did it, there was a little bit of a, holy crap, it totally works. And we see it. Because I still feel that way every time I see it. And I see it every year when I'm working with whatever version of class I've got in the lab. I still think it's really cool that it happens. But all right, well, so you've already seen it, but now you see why it's happening. But it's just interference. It's those waves coming together and canceling each other out. All right, so any questions on that derivation? Does that make sense? And hopefully that even helps you a little bit when you're looking back at your lab and doing stuff.
It definitely makes more sense now.
All right, but that was just Friday though, right? So we haven't had class since or anything. I'm not too upset about this actually. Now that I think about it, I think what I'm going to have to do on Tuesdays and say, what did you guys do in lab? Just so I know from now on. Or you can always tell me, it's never going to hurt my feelings. So, all right. So let's talk about another place where we see interference. And this was something that was brought up earlier when we were talking about rainbows. Remember when we were talking about rainbows and I asked about where you'd seen them, and a couple of you talked about like oil on the water, like, or if you look at bubbles, they show this as well, right? That's actually due to interference, and that's what we call thin film interference. So let's talk about this one. So this is still interference. It's just for a different reason. So let's think about like a bubble. So you've got a soap bubble and you're looking at it and you see the nice pretty colors, right? Okay, so why? Why are we seeing that? All right, well, what's happening there is, actually, let me show you a nice pretty picture. Let me switch share here real quick. Just so that we all know what I'm talking about. Right, so here's a great example of this. And so you see all kinds of different colors. You've got the purples and the pinks and the yellows, and there's a little bit of green and blue, and right. So we're seeing all these different colors, which makes you think rainbow, makes you think dispersion. But that's not actually what's happening here. It's not that those different light rays are coming at different angles and coming to your eye. If that were the case, we would see nice symmetrical bands of colors. And we definitely don't see that, right? This is all swirly and, Lord knows what. Okay, so it's a different reason, but this is what's going on with thin film interference. So here is a little film of soap. Okay, so this is our soap bubble, which means out here is air and on the inside is air. So that's just our little bubble of soap. Now, let's think about a light ray that comes into it. So we send a light ray in. What's going to happen to that light ray?
Gonna
Go ahead, Victor. What were you saying?
It would change the angle.
Okay, so it's going to refract, change the angle, and right? So it's going to do something like that. But what else is going to happen?
gonna do it again.
Okay, it will do it again. If we're going back into air, it'll end up coming out parallel to what it did before. So yes, there's going to be light that comes in, bends through the soap, and then bends back out as it comes to the air. But what else happens at this line right here, where the air and the soap meets? There's not just refraction.
There's reflection too.
There's also some reflection, right? We've seen that every time we hit one of these surfaces, there's reflection and refraction both happening, right? Unless you get like total internal reflection. But in general, you have both. And so then the same thing's going to happen here. You're going to get that bounces back up. And then when it hits this soap air layer, it's going to bend again. It's going to come out like that. Okay, yes, then there's also going to be a reflection here. And so there's going to be some light that just keeps reflecting back and forth between in the soap bubble. But the power, the energy in these, the intensity of these is going to decrease every time we have a reflection. So like by the time we were to come down and do a third one, that third one's going to be virtually invisible compared to the others. It's going to be super dim. Okay, well, anyway, so this is kind of what's going on. Now, The interference is happening because of these two. Those two waves, they're going to be really close to each other, especially if this is really thin. I wanted to exaggerate it a little bit to show but you can imagine if that's really thin, the offset's not going to be much. And so those are basically on top of each other. And it's those guys that are going to cause interference. So when you look at a soap bubble and you see, let's say, blue, what you're seeing is the wavelength that's not being interfered with, or it's not getting destructively interfered. It's getting constructively interfered. So then if you see orange, well, it's a different wavelength that's surviving the destructive interference versus the pink versus the whatever. Okay, so let's think about this in terms of what's causing that interference. Well, in order for it to interfere, and let's say we want it to cancel out, we need these waves to be exactly halfway out of phase. And it turns out that that can happen in two ways. The first is a phase change due to reflection. Sometimes when it reflects, it goes out of phase. Sometimes it doesn't. Sometimes it actually stays where it was. And we talked about this when we talked about waves last year. Remember the idea of like a wave on a string that's tied down versus one that's free to move up and down. I say remember like I expect you to remember, but we did talk about that. And it's kind of the same deal here, is that some of these waves are going to get a phase change due to reflection. Okay, so if we go from smaller n to bigger N, you're going to go out of phase. By 1/2 of the wavelength. So if you are coming in with a peak shows up, it gets reflected, it comes off as a trough. Okay, that's what I mean here. If you go from bigger N to smaller N, there's no phase shift. So that's the first thing that can actually lead to this interference. Like, think about what we've got going on here with this air to soap to air. I don't know what soap's N value is, but I know it's going to be bigger than air, right? The light's not going to pass through it as quick as it would through air. So that means that on this first reflection right here, we're going from smaller to bigger. So there's going to be the λ/2 change. If you look at the second one, I'm going from soap to air, so I'm going from bigger to smaller. This will have no change. So this is one of the things that can lead to the interference. But clearly, that's not the only thing. Because think about what this would suggest. If one of them changes by 1/2 of a wavelength and the other one doesn't change at all, what's going to happen when they come together? Is it going to be constructive or destructive?
Constructive, I guess.
So they were both at peaks. Now one of them is a trough.
Oh,
Eh,
yeah, destructive.
Okay. So those are going to cancel out. So what we would expect right there is destructive. And notice that this doesn't depend on the wavelength, because all the wavelengths, no matter what our wavelength of light was, we're going to get that same thing happen with that shift, which would suggest that everything gets destructive or destructively interfered with. What would you see in that case if everything got destructively interfered?
A clear bubble, right?
There'd be no color, right? In fact, you wouldn't actually see anything. It'd be dark. Right? But that's clearly not the case because we still see some things. So it's not just that that's going to matter. So the question then is, all right, well, what else is it that actually matters? Well, it's this piece of the journey. Because those two light rays have traveled a different distance. If we say that this film has thickness T, that second ray, the one that went through the soap, so I'm going to call that ray number 2. It actually travels a greater distance, and it travels basically 2t greater distance. So remember when we were looking at the interference of the double slit experiment, the two different rays traveled a different distance. And it was that different distance that led to either constructive or destructive interference. Well, same thing's going to happen here. This different distance, we're going to get either constructive or destructive if that thickness is either a whole number of wavelengths or whole plus 1/2 number of wavelengths. Exact same argument as before. All right, so what we're going to need to look at is this 2t either a whole number of wavelengths or is it whole plus 1/2 number of wavelengths? And that's actually why you see different colors on a soap bubble, because different parts of that film have different thicknesses. And those different thicknesses are going to either destruct or constructively interfere with different wavelengths. So all of a sudden it's like, oh, the color I'm seeing here is blue. That's because blue is being constructively interfered. The other ones are being destructively interfered. Off by like a quarter wavelength, you're definitely cutting down on how much of it is there. And so your brain is going to not see it as well. It's going to go, oh, I see blue. I don't see the red because it's really minimal compared to the blue, even if red hasn't technically gone away. So this is a much more complicated question because of the two parts to this. The difference in distance thing, yeah, that's exact same. That's same. But we also have to pay attention to what's going on at these reflections. Are we getting the changes in the wavelength or the change in the phase due to the reflection? So unlike the other one for the double slit, I'm not going to give you a formula because it turns out there are actually 4 formulas. instead of just the two. There's going to be, the first formula is where they both go through a, half of a wavelength shift because of reflection. And then we're going to have constructive and destructive in there. And then the other one's going to be only one of them goes through the wavelength change or phase change. And then you're going to have destructive and constructive. So I don't like doing that. I like just thinking about the idea behind it. Knowing that to get constructive, they need to be in phase. To get destructive, they have to be out of phase. And like what we're seeing here with the fact that the top one went through a phase change, but the bottom one didn't, is only because we've got air on top of soap on top of air. Right? Like what if we had air on top of oil on top of water? So this is, the oil in the parking lot after it rains kind of deal. Well, it's possible. I don't know what the end value is for, say, oil versus water, but it's possible that instead of the second one not having a change, I actually get a half a wavelength change. So we have to allow for that. And we have to pay attention to what's going on at both of those surfaces. Then you can turn to this. Okay, but to make matters worse, just because, why not? Yeah, the wavelength in the soap isn't the same as the wavelength in air. So if we shine, if we're shining a red light, let's say we got a red laser and we shine it in here, while its wavelength in air is, let's say, 650 nanometers, its wavelength in the soap is not 650 nanometers. The wavelength actually changes when we're in a different medium.
Did we just stumble upon a differential equation?
We did not.
Okay.
It turns out it's actually a really simple, like you can just use a little bit of algebra to get there. But it's something that we definitely have to take care of. So let me just share that with you, and then we'll call it a day today. But on Thursday, we'll pick up here and we'll actually do some examples. But here's what happens with the wavelength when you're in a different material. Remember how you get wavelength from frequency and all that good stuff? He asks, hopefully.
1 over frequency.
Okay, so lambda is 1 over frequency. And how does that relate to, say, the speed of the wave? Yeah. It's wavelength times frequency. Do you guys kind of remember that?
Vaguely.
Maybe, kind of, sort of. Right. So your velocity is your wavelength times your frequency. Wavelength is in meters, frequency is per second. So meters per second. Easiest way to remember this stuff is just to go to units. But anyway, so we have V equals lambda times frequency. So it's actually, lambda is V over the frequency. So let's think about in a vacuum. And we can say air is close enough there. So for light, lambda is equal to C over the frequency. If we go into a medium, the velocity is now going to be less than what it was in the vacuum or in the air. And we used N to get that, right? N was the ratio of C and V. So in the medium, V is equal to C over N. So that means the lambda in the medium, which I'm going to call L sub n, is equal to V over F, which is C over N over F. And if you just kind of fiddle with that a little bit, so we get 1 over n times C over F, which was the wavelength out in the air. And so that's how the wavelength changes, actually. So when we look at the wavelength of the light in soap, it's actually not going to be the same as the wavelength it was out and about. We actually have to divide by the n. And the reason that that's going to matter is, remember this bit that I have in the orange where I say ray number 2 travels 2t more distance. And I say we're going to need to see if that 2t is a whole number of wavelengths or a whole plus a half number of wavelengths. That has to be the wavelengths in the soap, which are different than the wavelengths out in the air or the vacuum. So even though it's still interference and it's the same idea of constructive and destructive, it's incredibly more complicated because A, we have to deal with the reflection and pay attention to phase changes there, but then B, our wavelength changes. Well, have no fear. We're going to go ahead and just use that and kind of follow through. We're going to get a nice little formula that involves the wavelength in the vacuum of the air. So we don't actually have to worry about the wavelength. We don't have to convert it. That will be taken care of in our formula, but it is something that we do have to pay attention to. But we're out of time for today. So that's my hook for Thursday, is to, we'll talk about, we'll continue with this and we'll talk about interference with soap bubbles and the like. But a couple more things before we call it a day. Again, no homework due tonight. I'm giving you till Thursday, but I do want to have quiz number 2 on Thursday, and it's going to be on chapter 2. So chapter 2 again is all the geometric optics. So expect quiz 2 to have things like, you know, here is an object in front of a mirror. Where is its image? Same thing with lenses and stuff like that. Okay. So we'll have our quiz on Thursday, same story as before. You'll go ahead and start it at class time at 4 o'clock. And then we'll meet in here at 4:40 and we'll talk about thin film interference. We'll do some more of it, I'll review it, and then we'll do some examples and we'll just kind of run from there. All right. So with that, I'm going to wish you all a wonderful couple of days, except really I will see you all tomorrow in Diffie Qs.